Well, that's a big pleasure being here once again, which is beautiful. I'm honored to be by delivering this course. And I want to start with so, we are going to be working with Discrete for the version of what we're doing. So, in order to have a better idea of what this is about, structure, let me just make a very brief review of the idea in class Morse Theory. But throughout the course, I will be assuming that you are familiar with like topology, fundamental groups, and discovery phases, and things like that. Okay, so what is the story about? So the idea is one can understand the shape of a man. One understands a family of typical functions, smooth functions, defined with values on the real field. So actually, any one of a single such typical such generic such function is able to recover the complete topology of the manifold. And here's a very complete picture. So suppose you have this norm. This is just the surface of the curve. It's not solid. And we have this sort of stand it up in this way. So we have this function which is just the act of the. So what is the idea here? Well, if you think of the function as a scanner, every time you look at the index, and as you scan the different heights, you will be seeing how this is made. But there are some special points where the topology of this scanning thing will be changing radically. So, for instance, we can take a look at the function. The first where the function the infinitesimal values of the function, the difference of the function does not change. In other words, the point where the tangent plane is horizontal. So in this picture, for this high function, we have four critical points where the tangent plane is horizontal. And, well, of course, one has points, critical points, 4 points, but they don't have any kind of topology so far. They are just zero-dimensional, they are just points. So one needs to understand a little bit more of the topological information that they have. And, well, one can introduce the index of this point. And what is the index? You can think of a little chart around these points and essentially look how this function behaves in this neighborhood of this point. And essentially, you can make a change of a basis, and for instance, in the first point, we will have that the function behaves like a sum of the first of the two variables that it has. This is a two-dimensional surface. So, and essentially, in the neighborhood, the function behaves like a projection x1 to the square plus x2 to the square. And this essentially tells you that if you move in the two independent directions, the function will be increasing. Now, the next critical point is a little bit different. There, the function locally looks like x1 squared minus x2 squared. So essentially, x1 will be the direction coming perpendicular to the screen, if you see this in that way. And there, the function is going up, like a parabola. And x2 will be parallel to the screen, where the function is decreasing. So essentially, we say this point is of index 1. By the way, these numbers, this form, what you say is you count the numbers of directions, linearly independent directions that the function is going down. So in this case, in the first point, there are no directions for the function decreasing, so the index is 0. In the next case, there is one direction, because here, where the function is decreasing and the other one is increasing, essentially. And so these 2 points have index 1. And the very top one is a point of index 2, because, well, you can see that locally the function behaves like a negative of what is happening on the bottom, critical point. All right, so, well, now we have associated this idea of the index, which is an integer, for these 4 critical points in this expression. Now, what's the point here? The point is that, well, let's reassemble, let's understand the topology of this picture, of this manifold for critical points. And what one does is, well, you take a look at what is called the sub-level surface. So, for instance, choose a height and look at the inverse image of that, of all the points in the manifold that have at most that height. So in this picture, it looks like this cup. And not only that, one interesting thing is that if you look at the gradients arrows, namely those directions pointing into the direction of maximal decrease for the function. In other words, if you put a drop of water in one point, it will just follow these lines. Well, this information tells you how you can deform, if you care about the topological information up to homotopy. This line tells you that this sublevel surface is essentially contractible to a point, and of course the point has dimension 0. And so the index of that point is 0. So that's fine. And if you vary a little bit this height, you will see that nothing really strange will happen. The only thing is that this height will be increasing or decreasing a little bit. Topology is essentially trivial, that one of a point. But once you pass this critical point and say you look at some height, if you are at height B or higher, then the topology of the thing changes radically. And for instance, in this case, the inverse image of this point will be something that looks like that. Now, one can take a look at, again, with the gradient lines to try to understand this topology of this thing. Well, in this case, forget about this line, which is the orange line. Just focus on the level of this height, the green stuff, and follow the deformation that follow these lines, these gradient lines, to deform it. So essentially, what you're doing just is pushing down the two legs of this half curve, and well, essentially, as you can imagine, this point goes into here. Some points in here go like that. This point goes into here. There is a problem here because this point doesn't know where to go. Either actually, this is critical. If it is, it will stay there. So essentially, although these points want to come down in this way, they will try to do it a little bit, but just keeping them on the top of the point. So because we don't want to break the space, we only care about the formations of the homotopy, but without changing the topology. So essentially, the whole thing deforms back into this picture, like this cup with a handle. And this handle is, of course, a cell of dimension 1. And it is the same dimension as the index of this point that you eventually cross. So the index and the gradient lines tell you how you are assembling up to homotopy this, at least up to this point, this space. And of course, once you are in this green cup with a handle, you can just keep on doing this deformation, and it will just tell you that what you end up at the end is a point accounting for the cup, and then a circle, stretched circle, which is essentially just point and a cellular structure of a point and a one cell. So this is just a circle. So what we have up to here, up to homotopy, up to here, sorry, is a circle. It's quite clear, you can see here. All right. Oh, make topology would say we just crush this half torus in this way, and you will get this result. All right. Now, well, you can just keep on doing this. For instance, when you pass this critical point, also dimension 1, and you look at these kind of surfaces, the story will repeat. It will tell you, the flow lines will tell you how to perform to get the previous shape, namely this one, with this guy, with another cell of dimension 1. So up to homotopy, we see that at height C, we have essentially 1 point, and 2 circles. Notice that in order to see the most efficient picture of this manifold, you just have to keep on doing the thing. For instance, when you do this deformation, you end up with this thing, and you already are starting to see this thing. But then if you continue doing this deformation, then this guy will be just assembling this point and making this new circle. And then you can just continue the whole picture from here to here to realize that you will have a point, a circle, and another circle attached to it, like a number 8. And at the very end, when you reach this height or anything else, the higher, you are essentially attaching what you need. Just as before, we have cells of dimension 1, and at the very end, we have a cell of dimension 2. And that agrees, of course, with the index of this critical point. The index of this critical point is 2. So this is basically how you can think very roughly that a discrete, classical smooth function defining this manifold recovers the topology through these deformation lines. All right. So the point is that, here you can see what you're doing. Essentially, at height C, one has this picture, and then one is adding two cell, and which is attached in the usual way. If you follow the picture, you will see that essentially you are following one of the circles first in the same direction and then in the opposite direction, and the other one the same. It's actually quite clear if you look at what's happening here, because how is this circle attached? Well, essentially, if this circle, which is essentially this one, is going, this point goes through here, and as you move in this direction, you will be following, as you move in this direction, you will be moving in this, like this, and then going back into here, and then like that. So notice that the first one, this goes to the left, and this goes to the right. This is one of the ways that it is attacking. And the other one, you have to go like that, and like that, and then continue, and continue. So here I'm going this way, and here I'm going this way. So when I collapse this half form, you will see that you get the other attaching maps in the other side. Just recovering precisely this the standard picture of the core with a two cell attached to it. Okay, so this is what is happening. And the whole point is that up to deformations, up to a homotopy equivalence, we recover the homotopy type of our manifold case as some cellular complex that I'm denoting here as Morse M. And this is a cellular complex, namely it is made of cells, it is made of points, lines, 2 cells, 3 cells, and so on. In this case, I only did what I described. And this is quite efficient in the sense that, this Morse complex has as many cells in a given dimension as critical point had the function of that index, of that dimension. So in our case, we have a critical point of index 0, 2 points of index 1, and a point of index 2, which means that then this, in that case, we have the standard construction of the torus, namely a point, then a number 8 made of 2 1 cells, and then a single 2 cell. And the point is that one recovers the homotopy type of because we can recover it. We have all the information needed to recover the topology type is encoded by the gradient flow of this function. So this is the whole point of the idea of discretizing this business. And by the way, one can, well, if I have a homotopy equivalence, I should be able to use this machinery to compute homotopy invariance of this manifold. For instance, the classical one, the standard one, would be, well, look at the homology. And you recover the homology of the torus, or in general of the manifold, from this information. The answer is yes, because you recover the whole homotopy type. And essentially, you do the same thing. When you compute homology, where you say, well, here's a cellular structure or a triangulation or whatever. And, well, I take the chain complex, the chain complex or co-chain complex. I can dualize it if you want to compute homology or cohomology. And then I have to define boundary maps in between chains of dimension n to chains of dimension n-1, and you do the standard business in homology. Here, you can do something similar by just using the information that we have to start with. I can form this chain complex, but it's not defined in terms of cells by itself, but by critical points, because critical points have the information of the cells at the end. So what one does is, well, take in dimension 0 all the free abelian groups generated by those points of index 0. In this case, there's only one type. And so in index 1 and in index 2, we have two, respectively, we have here two points of index 1, and then we have the very one on the top of index 2. And then one has to define the analog of the boundary operators between the cellular chain complex, the classical cellular chain complex. But now we don't have cells. Actually, we have critical points. So essentially, what one does here is, well, one has to compute the number. If I want to understand what's the value of these operators in this generator, I have to understand the number of gradient lines going from that generator into the other generator. And recall that here the generators are critical points. So I have to go back to the picture and say that this generator accounts for this generator in dimension 1. So I need to understand how many gradient lines there are from the index 1 critical point to the 0 critical point. Index 0 critical point. And in this case, there are actually only 2 lines. If you draw that, so in that case, remember that we have that, like that, and I want to understand the boundary operator from this critical point to this critical point. So I have this one and the one that goes in the back. And essentially, what you have to do is count the number of these lines, but taking into account orientations of these lines. And these 2 lines are parallel, although in opposite directions. So there is one, but then you're subtracting one. So all in total, what it amounts to at the end is that the image of this generator under this operator, boundary operator map is trivial. It would be 1 minus 1 times the index 0 point generator on the other side. So, and if you do this business for each of the generators, you will see that in this particular case of the torus, you recover, well, you will realize that this boundary map is trivial. And this is very good because if you want to understand the compute homology of a chain complex, which has trivial boundary operator, yes, you have to do nothing. Everything is in the kernel, nothing is in the image, and the homology would be on the node what you see here, the standard. So there is a generator in dimension 0, taking into account that this has one piece. There are, I don't know what happened there. Great. So you recover the homology. The homology is a typical one. And one point to keep in mind here is that this function, this high function, is very efficient as it has the minimal possible number of critical points, because I can produce this cellular model for this manifold, the toroid, which has the less possible number of critical points possible. Because of the homology, you cannot have anything else because the ranks will not match when you describe it. All right, so this is basically the whole idea that what uses in the classical, at least what we are going to be extracting for the purposes of this defining and using the discrete version of this thing. All right. Now, of course, this the main idea in discrete Morse theory is really not very new. It actually started at the beginning of the previous century with the beginning of algebraic topology before the 1930s, where they did the topology that they were doing were more like an simplicial terms. But unfortunately, back then they didn't have computers and they didn't have the technology that we have now, and many computations would not be possible to do just simply because it's too large. So, of course, then, well, if you don't have technology, then, well, humans have brains, and they came up with a very nice, beautiful mathematical theories, like the one that I described, that essentially allows you to do this in an efficient way. You have a whole toolbox for computing this kind of invariants for geometric objects. But now, ironically, we're back to this point where now we are with this technology of computers. Now we can put a computer, let's put a computer to work, and well, somehow we came back to this business of doing more computational stuff. And the idea of discretizing the previous technology is not really introduced by this guy, Robin Foreman, that is a work close to just a little bit before the 2000. Some previous people already had these kind of ideas, but in a sense, this is the typical reference that were developed in more systematic way, this theory. So what's the main idea? Well, in the classical situation, then we have critical points with indices. Now, if I want to work these ideas with a simplicial complex, because we have a geometric realization of an abstract simplicial complex, well, we already have cells, and cells have a given dimension. That's what we have. So, well, suppose that this is part of a simplex in a huge simplicial complex, and I would like to understand how this is attached to other cells in order to assemble some topological information. Of course, this is typical when you want to understand geometry. You want to understand information in terms of the geometry. That's some topological construction that you do out of some databases. Well, let's introduce what would be the analog of this high function. Before I had some smooth function, there's a lot of geometry there. I'm not going to be caring about geometry. I want things to be discrete. So I want to say what's the height of every point, but not in a continuous way, rather in a discrete way. So let's think of the barycenters of each of the cells in this triangle. We have 3 cells of dimension 0, which are their own barycenter. Then we have 3 cells of dimension 1, and think of their corresponding barycenters, and then a cell of dimension 2 in this case, and assign a height to one of these barycenters, or equivalently, a height to each one of the cells. Now, here's a picture of what you have here. Essentially, this guy is the highest point is of height 14, and then this would be the next. It's a little bit going in this direction. You go down, this is a little bit even below, and so is this. And essentially, you can just take a picture and make it. Now, what's the idea? Well, this assembles the idea of a critical point of index 2, because it's a maximal. This is a maximal point, and you have essentially two directions of decreasing this function. Now, suppose that this guy is attached to this guy, and of course, you have to preserve the heights of the points, the corresponding points. So essentially, I'm attaching this guy to this guy and making this identification here. But now this has different distribution of heights, as you can see there, and this amounts to this picture. Now, if I want to follow the idea in the previous equation, I need to follow the deformation lines. So I need to introduce this idea of the forming of these gradient lines. And well, here there's not much I can do because essentially this point cannot move. This is a maximal point. But in this situation, well, you can see this triangle is like in this shape. And it would just, if you put a drop of water in each of the barycenters, it will follow the lines that you see in red there. So that would be intuitively the discrete analog, the analog of the lines. But of course, we don't have geometry here. So essentially what we are doing is saying, okay, well, what is happening is that this guy wants to be friends of this guy, with this guy. So in a way, they pack together. They form a friendship pair. And so this pair of points, and so this pair of points. And over here, you cannot this kind of relationship, friendship relationship, because you cannot say, well, I cannot make this pair, or for instance, make this pair, because there is no real reason for doing that. This is just on the top. And instead, you can do this, and then, well, here you have the essential idea of how to discretize and produce the idea of a gradient field, namely these kind of lines. And of course, these lines recover the whole idea on how you can deform this local cell down to a point. But in the process, recall that this is not isolated. This is attached to the top one. So if this thing is going to be deforming like that, say topologically, well, then you better, these points will be also following that, and then this whole cell will be stretching to follow this deformation. So there are some cells that are going to be deformed, some other cells that are going to be collapsed, some other cells that have to be stretched just to keep the information, and some cells that whose only job is to say, well, I'm going to be in charge, namely this cell, I'm going to be in charge of collapsing this other cell. So one will have three types of cells. Those that are really stretched, and I'm going to be keeping the homotopy information in the whole picture, and then the cells that are paired, that form a pair in different ways, saying I'm going to be pushing it and collapsing another cell. So this is essentially what is behind the whole thing. And here's a very naive example of what can we look here. So here's a pentagon. This is a disc. This homotopically this is a disc, but in the shape of a pentagon. So it has 5 2 cells, then it has like 10 1 cells, and then has 6 0 cells, if I make my counting correct. Now I want to follow the same idea there. So this is introduced like a something planar. It doesn't have any height associated to it, but I can make this procedure of making pairs of consecutive, some of the consecutive pairs. And for instance, I can introduce this gradient field that you see here. Namely, this guy is going to be paired with this guy, and so on. This guy is going to be paired with this guy, and so on. Essentially, what this suggests is that this line is the highest one of all of them, then you will have this, and then you will have this, and so on. But I don't want to associate a number. It wouldn't really matter to say this is high 10 or high medium, whatever. It just I want to tell you that it will be flowing in this direction. So, well, then you can, just as in the case of the example of the torus, where you simplify the cellular structure, the homotopy structure, into something similar. If you do this stretching business, you will get that from here, if I, for instance, push this cell and deform it following these lines, I would essentially just stretch this cell to occupy this area. And then I just keep on doing the same until I get to this cellular structure. Notice that there is, in this situation, there are one two-dimensional cell, namely this guy, and then there are some two-dimensional cell, two-dimensional cell. Then there are a few one-dimensional cells and a zero-dimensional. Now, one thing that I would say, okay, let's just keep on deforming, and suppose that I want to introduce an additional information for deforming this thing. So I would like to push this and deform it somehow into something that looks like that. But of course, in all this information, this point stays here, and this point also stays in there, and the rest has to be pushed. But it cannot be possible because the whole line that you're pushing is connected. And at the end, you will have to put it into a single point inside a pentagon. And this is disconnected. So topologically, this is not possible. So something goes wrong with this naive idea if I just try to keep on pushing things. And what goes wrong is that you then have a cycle, if I wanted to do that. And in a cycle, it doesn't make sense because recall that these lines say, well, this is going downwards and downwards. And if you just keep on going downwards, you cannot go back to the same point unless you are Escher, of course. But here we have no those crazy things. So the idea is one should be avoiding cycles in this way of pairing things. Instead, we can, well, if I already have this gradient field, I could say, well, if I do this, I get into trouble. Why not, for instance, deforming this into this direction, which would be making this deformation and to get to the next image. And the business is simple from that point, because then you can just make this other gradient field that looks here in orange, and get at the end, at the very end, a point. And of course, you recover the homotopy type of this pentagon, solid pentagon. So this is a very strange way of saying, well, this pentagon is contracted. It's a stupid way of putting this, but it's a systematic way. And many times your simplicial complexes are not so simple as you would see in the other. The whole idea is that you want to do this algorithmically, and for things that are really huge. And even if you have computers, you want to simplify your work and be able to do it. So at least this gives you a recipe for understanding homotopy information up to homotopy of the whole thing. And of course, in data science, topological data science, and stuff like that, essentially the idea is you want to understand the geometry behind these geometric objects associated to information. So, well, that would be the idea. Now, let's take a picture. Let's go back to the torus. What happens in the torus? Something is there, but it's not showing here. So you want to, okay. So let me just tell you, the point is, given a simplicial complex, you want to be able to produce a gradient field. This way of associating. I'm going to be a little bit more formal in the next talk, but this is basically the whole idea. You want to have this gradient field, which is this kind of friendship, one-to-one relationships. And how to do that? Also in a systematic way. If I have that, then I have the information to understand up to homotopy homotopy invariance of our signature function. But there is a point: how to produce discrete gradient fields in any general differential complex, or for that matter, in some cubical complex or something discrete that you have that has information. Well, I have to say that producing discrete gradient fields is a difficult problem. It's a hard MT problem, but there are some algorithms. If they are expensive, I'm going to tell you a little bit about them later in other sessions of this talk. But here is what you would produce with one of these algorithms. So essentially, this tells you which ones are higher than the neighborhood ones and how they are started forming. And well, I just pull out of the hat this thing, but this is going to be important when we formalize ideas. All right, so I want to, here's a torus, and here's a gradient field. This is the time that I select? Yeah, all right. So I have this torus, and I have this gradient field. So let's see how you're deforming to recover the standard picture of the torus with only 4 cells. Well, these kind of cells are the ones that are not needed, well, they are redundant in the sense that they only are needed to collapse some other cell. In this case, this cell is going to be collapsing this other cell. But there are some cells, like in this case, the green one, which are not associated to anything. They are just keeping the information, the basic information of the topology. But you need to understand how they are being stretched to occupy the rest of the cells that are important, the critical ones. And you can do this following, just as in the case of the torus, where you follow the gradient field to reassemble the homotopy. Here you do the same thing. There are critical lines, and they are observed like that. For instance, this guy is going to be deformed in this way. So essentially, half of this line is mapped here, and the other line is mapping to here. So in other words, this guy becomes this guy after making this deformation. And a way to keep I don't want to do anything topologically, I want to do this combinatorially. So essentially I say, okay, this guy goes like that and also like that. This is a continuation, this is what is called a gradient line. It's a cell associated to something, and then you exit through one of the remaining phases, either this one or this one, and then you just keep on doing. This goes like that, and then you have to exit either for one of these two guys. Now, for instance, if you follow this line, once you are here, well, you have the option of going this way. But notice that this guy is going to be collapsed to a point. And you started, of course, in a set of dimension 2. So this guy, part of this guy, a little bit of portion just goes into this point, essentially by following these deformation lines. But if I want to understand homology, you only need to understand how n-dimensional cells and their boundaries attach to n-1 dimensional cells, not lower, because homology doesn't care about that. So essentially, you have to forget about anything that ends up in something that is collapsible, because it goes down in dimension more than two or more. So essentially, that what this tells you is this guy, part of it, how is it distributed? Well, it goes, for instance, like this. It is assembled in that way. And part goes, let's see, here's another one. This is one. And here's another one that goes like that. Oh, this is another one. Let's see, this one goes like that. And here's the other one going like that. And in the blue lines, I'm just recalling the orientation purposes, because when you compute homology, you have to take into account the orientations and see how the boundary, the inherited orientation of the boundary, how it attaches to the other cells of some given orientation. So if I are orienting these two cells in this way, so this is the orientation of this part. So let's just follow that. If that part goes like this pen, and then when you follow this line like that. No, the one that is easier is just following this line. It would go like this. It would go, it starts like that, and then moves like that, and moves like that. So it accounts for the top blue line in there. So this is how it's mapped, essentially. And if you look at the other one, if you look at there's another, let's see, there's another guy that goes in here that is mapping to here, and you do the same thing. If this is oriented like that, namely like that, then it's oriented like that, and then this is oriented like that, which accounts for this thing. So this tells you that part of this cell is attached to this one-dimensional cell, one time in this direction and the other one in this direction. And you can do the same thing for this, for the other attaching map, and you will see that you essentially recover the classical picture of this square with lines identified. For instance, if you go one lower dimension, you have one critical point, you have one cell that is attached very easily here, and also attached to this, and this gives you kind of a horizontal line up to the identification, because this point is this one, so this goes really a circle. And then this guy, which has to stretch like that, and like that. And this gives you the vertical guy to make you the one-dimensional skeleton, and then you attach this two-dimensional cell, following what I already said, and you end up with the same classical picture. All right, so this is what you can do. You recover, well, it is possible to define then this Morse critical complex given by not the free group, abelian group on all the cells of the complex, only those that are critical. And then following these gradient lines, you have a boundary homomorphism. And then you would just compute the homology of that. So the idea here is that you want efficient gradient fields that leave you with the less possible number of critical points, critical cells, because then at the end, these are the complex that you want to work with and compute the homology. All right. And of course, the one has this theorem. If you have which is quite transparent here, if you have a simplicial complex A and a gradient field, you've been able to produce a gradient field, then the homotopy type of your the original complex is actually the same one of the one that I just described. Namely, just recalling that you have critical cells that are going to be stretched, and then other cells that have to be pushing to collapse in other cells, and at the end you get this very simplified version of the homotopy type of that. And in particular, well, you can just say there is a isomorphism. You can compute the homology of your original simplicial complex in terms of the homology of something which is smaller. All right, so I guess this is a good point. There are some other, yeah. I have 5 more minutes.
Yeah.
Are there any questions up to this point?
Yeah, I have a question. If I have a simplicial complex, but expressed with its maximal simplicity,
It's
expressed
okay.
with the maximal simplicity, those simplicity that doesn't have any place. It should be more easy to reduce the critical points from there. No?
Yeah, yes, of course. I guess you're talking about having 3 phases of the simplex. Exactly. If you have some simplex and you have part of this boundary does not have any, if I understand correctly, there's no other sequence on the side. So this is a free phase. You can actually do this for pushing in this direction.
But what I mean is the whole maximal simplex. The simplex that is phase, that is co-phase of that free phase.
You understand, right? So you have the facets, the maximal phases.
Yeah, exactly. That's what I mean. Then if you have the simplicial complex with the maximal phases, in each maximal phase, you will have three phases.
Yes.
So it's more easy to have that instead of the word simplicial complex with all the phases.
Are you saying at the very end, if I have only one triangle with its whole things?
Yeah.
Well, it depends. It's what you involve is really is simpler in some sense because it has less cells than what you started with, which can be huge. But at the end, you recover this. The point here is that at the end, you recover the incidence of numbers. How do you want to understand how what the critical cells attach to some other critical cell? Even if the attaching map is complicated, but if you are able to recover the incident numbers, that is all the whole you need to recall to compute homology. And if I understand correctly, your question is I started with something that is huge, but the information is simple in the sense that it's time related. Okay, the computing incidence numbers is easy, but then there's a lot of information that you have to process. And that's at the end, in the long run, it is more complicated. I hope I have to.
No, thank you. Yeah.
Are there any other questions?
Yeah, I do have one question. Is it?
With the microphone, please.
Is it on? Hello?
Sí, yes.
Okay. So, is it possible for a simplicial complex with no free faces to be collapsed in this sense to something without faces of higher dimension, like for example, if you have a two-dimensional simplicial complex with no free faces, is it possible to collapse it with something without two-dimensional faces? Yeah, for example, the Down's head or something like that, which is contractible.
But in that case,
But you don't have any free faces, but is there a field?
I'm thinking of
allows you
this
to collapse it
example,
to
but
one point?
unfortunately, it does have mechanism. But see, it might happen something like in here. If I only think of these, I make these deformations out of no free faces. For instance, this one is not a free face of this guy.
Okay.
And so on. This guy is not a free face. So the very first deformations just are increasing lowering the number of two cells. But still you're making deformations out of no free faces.
Yeah.
But in this particular case, at some point, if you want to keep on deforming this, you would have to use necessarily a free face. But yeah, I depending on the topology of the simplicial complex, it might be possible that just doing that procedure with free faces to reduce up to homotopy to reduce
The dimension of
the
the
dimension.
simplicial-
It might be possible. It should be really possible. For instance, in the case of the torus.
So it's not necessarily so you don't necessarily need free faces to be able to reduce the dimension.
No. I don't see any reason why if the existence of free faces on some facet implies the non-existence of free faces on facets would imply that the homotopy dimension would have to stay like that.
Okay.
I don't see that. I don't think that's
good. Okay.
and that's a good point because one of the there are some algorithms for producing gradient fields. And of course, the use of Discrete Morse Theory to computing these things and doing the topological data analysis is now well understood. But of course, if they want to do that, one needs an algorithm. And there's an algorithm essentially that is based on that thing. Essentially, if you find a free face, push another free face, push, and so on, until you run out of somehow free faces. And then you say, okay, I don't want this top dimensional cell. You just remove it, you declare it that it is critical, remove it, it will leave some free faces and just continue until this repeats until you hopefully can reduce the thing. But in that algorithm, you would be forced to keep in that dimension as of a critical thing. But it doesn't, there might be another ways of producing discrete gradient fields that are better than that. And this is one of the algorithms I want to be telling you about in at the end. It's not based on this co-reduction process. Thank you. So let's just, I suppose I can make a stop here.